In this section, we're going to work with springs colliding into things, and we're going to see what kind of excitement we can get from this. So this scenario here is a 2 kilogram block sliding on a surface, and there's friction on the surface, and oh my goodness, it's going to hit a spring, and we want to know how far the spring's going to compress. So let's just kind of like draw this thing, and here's my block. And let's see, we know that our mu k here is this 0.30. And let's talk through some of the traps that many students find themselves in. And one of them is they get hung up here. They draw exactly what I've drawn with this block way the heck out there, nowhere near the spring, and you fixate on, you're like, okay, so I know what my initial velocity was, but how do I know how far it's gone to figure out what's happening when it hits the spring? So let's talk about that. In this picture, you're told that there is friction on this whole surface. And this block has done all sorts of things, but what's happening is in the tail end of it, let's draw that spring out a little bit further, it's colliding with the spring. It's at this moment that it's going 1.3 meters per second. So what we don't know is what this distance is that the spring is going to compress, this delta x here. So let's see what we can't figure out from that. So initially, when I first come in contact with this spring, I have kinetic energy. What's that kinetic energy going to go into? Well, it's going to go into work from friction plus my spring potential energy, so I'm compressing it. I'm going to come to a stop at the end. So I don't have any kinetic on this side of the picture. And then I can go ahead and say, let's write this over here that I have kinetic energy then minus the work from friction equals the spring potential energy. And this is one of those things that I keep walking everybody through as far as, well, did I put this on the right side? And it just kind of depends on your perspective. So remember that this is the work from friction is going to be the force due to friction times the displacement times the cosine of the angle between. So friction force is going to be coming out, let's make that a darker color. It's going to be coming out this way. It's opposing the direction of the motion. And my displacement is this way. So that's 180 degrees. So let's think this through. If I write that out 180 degrees, that means that I'm going to have minus force of friction times the displacement. Now minus and a minus, so that says that I would have kinetic energy plus the work from friction, or the force of friction times the displacement. Well, that doesn't make any sense, because what that is saying is that the work from friction is actually adding energy in to compress the spring. So when I word my what is this energy going into, when I do it this way, what I'm actually doing is already accounting for the fact that my work from friction is taking energy out. So this is the correct expression if I take out the cosine theta. If I want to leave everything in because I'm nervous about doing anything without having an explicit equation, then I would want to say my kinetic energy plus the work from friction is going to go into my spring potential energy. And in doing it this way, I am letting the cosine of the angle tell me if I am losing energy or gaining energy. But I think for some, it is just kind of easier to think of it in terms of what's adding energy in and what's taking energy out. So at any rate, let's write this neatly over here, where we have then kinetic energy, and I'm going to explicitly write it without the angle, minus the force of friction times the displacement is going to be my 1/2 kx squared. And now I know what this is. This is what I started with. This is my 1.3 meters per second. And the force of friction, well, I can do a free body diagram and I can look at this and be like, okay, so I got force gravity down, force normal up. I'm in motion, so the force friction does equal the force normal times mu. And the force normal, well, in the y, I don't have anything pushing me down in the y, so the sum of my y is going to give me, let's see, if I define up and to the right as positive, it's going to give me force normal minus the force of gravity equals 0, or that my force normal does indeed equal the force of gravity, which is just mg. So now I know that this force of friction is going to be mg mu. So I can rewrite this in terms of what we have. I have my 1/2 mv squared, those are all known quantities, minus my mg mu. Well, what is this d? Isn't this d just this distance delta x that the box is going to travel as it's compressing the spring still over the friction? So my mu is just a delta x, and that's going to equal my 1/2 kx squared. So I know what my k is, and now I'm kind of regretting. I moved this to the wrong side of the equation. I want to move that back. So let's do that. My 1/2 mv squared equals my mg mu delta x plus my 1/2 kx squared. Now I feel like I can factor some things out, right? I can factor out, ooh, can't I? I can't. So it looks like I'm going to have to turn these and these into values. Ooh. This is screaming that I'm going to have something like this, 1/2 kx squared plus mg mu delta x minus 1/2 mv squared equals 0. So what do I have to do here? Well, this is A, this is B, this is C. That A squared, oops, the quadratic equation, my brain just totally stopped on me. So this is the 1/2 x, I'm sorry, 1/2 k is going to give me my A coefficient. My mg mu will give me my B coefficient, and my 1/2 mv squared, that's my C. So I can put that into my quadratic. So let's simplify this. I have 1/2 of 120, so 60 x squared plus 2 times 9.8 times mu, which is the 0.3, times delta x minus 1/2 times times 2. So 1/2 times 2, otherwise known as 1, times v squared is 1.3 squared. So see what we get. So here's what we get. I put this into the quadratic solver, and I get two values. I get this negative 0.224 and this 0.1258. And for my compression, the thing I want is actually this positive value, not the negative one. You can think of it as the negative one would have me end up like on the other side of the wall. I just keep on chugging on through. So I'm going to compress it by this 0.1258, otherwise known as about 0.13 meters. And there you have it.